Greetings, everyone. This is Professor Roman. Let's continue the group theory lectures. We are talking about normality, and I want to talk a little bit more about gigantic subgroups of a finite group. We have seen earlier that every gigantic subgroup is normal in the full group. Also, if M is a gigantic subgroup of G, and we take an element of G that's not in M, then G is the disjoint union of M and the coset AM. This is because the quotient group G mod M has size 2. It only has two elements, one of which, of course, must be the identity element, and that's the subgroup M itself. And so if we take any other element not in M, it will generate a coset. It will represent a coset, and it must be the only other coset in the quotient group. Gigantic subgroups also have another very interesting property, and that's described in this figure here. So M is a gigantic subgroup of G, which means it's half the size of G. Then any subgroup S of G is either completely contained in the gigantic subgroup M, as S1 is here, or it is half in and half out of M. It cannot be entirely in the coset AM. Actually, that's quite obvious because a subgroup has to have the identity element, and the identity element is in M. Okay, but the issue is, why does it have to be exactly half in and half out, or completely in? So here are the details in a theorem. It also includes our earlier results. And I called this the gigantic subgroup theorem. I wish I could think of a better word than gigantic, but as I discussed before, monster is already taken. That would have been a nice choice. So let M be a gigantic subgroup of a finite group G. In other words, the index of M and G is 2. Quotient group has size 2. Then the following holds. M is normal in G. The quotient group looks like this for any A that does not belong to M. And so we have this decomposition or partition of G into two blocks or two cosets. M also contains the squares of every element of G. If A is in G, A squared will be in M. And then every subgroup, S of G, satisfies one of the following. It's either contained in M or it is half in and half out of M, so that can be described in terms of the size of the intersection. S intersect M, it's 1/2 the size of S. As to proof, we just need to deal with parts 3 and 4, because we've already done the proof of the others. For the quotient group G mod M has order 2. So the non-identity element has order 2. So if we take any element of the group G that's not in M, this coset is the non-identity coset in the quotient. It has order 2. So A squared M, which is always equal to the coset AM squared by the coset product rule, since AM has order 2, its square is equal to the identity, which is the coset M. And this implies that A squared lies in M. For part 4, if S, our subgroup S, is not contained in M, then it has an element that's not in M, and so this set product is bigger than M, strictly bigger. But because M is normal, this is a subgroup. Remember, we discussed the set product when it's a subgroup. It'll be a subgroup if and only if the factors permute. If one of these factors is normal, then these two will permute. So the situation we have is that M is a proper subgroup of Sm, which is a subgroup of G, but since M is a gigantic subgroup of G, there's no room in between. So Sm actually has to be G. We also have a formula way back in chapter 5 that tells us how to compute the size of a set product. The size of Sm divided by the size of M is equal to the size of S divided by the size of the intersection. But Sm is G, so this size is 2. And so the size of the intersection is half the size of S. Here's an application of the gigantic subgroup theorem. It's a big help in analyzing the subgroup structure of certain families of groups, including the dihedral groups. So for the dihedral groups, D sub 2n, the gigantic subgroup theorem tells us there are two types of subgroups. The reason is that the subgroup generated by the rotation is gigantic. Rho has order n, its subgroup has order n, which is half the size of the group. So the gigantic subgroup theorem tells us that there are two kinds of subgroups in D2n. There are the subgroups that are completely contained in the gigantic subgroup, but the gigantic subgroup is cyclic, and we know exactly what its subgroups look like. There's one subgroup of this form generated by rho to the n over d. It has order d for each d dividing n. So that takes care of the subgroups of D sub 2n that are contained in the gigantic subgroup generated by the rotation. All of the other subgroups, S of D2n, are split in half by the gigantic subgroup. And the portion that's in the gigantic subgroup, the portion of S, so S intersect this gigantic subgroup, again is a subgroup of this cyclic group, so has this form. Therefore, the entire subgroup S is the disjoint union of the portion that's in the gigantic subgroup and a coset of that, a non-identity coset. So A times that portion of the subgroup that's in the gigantic subgroup. I know that's a lot of words. I hope that's making sense. Maybe I should speak more slowly. So A belongs to the subgroup, but not the gigantic subgroup. And that means this coset is not equal to this. Now, any element of the dihedral group has the form sigma rho to the k. And k is in this range 1 to n minus 1 because rho has order n. So S then takes this form. But now the question that must come to our mind is, are all these subgroups distinct for different values of d and k? It's a complete list of subgroups, but there may be duplicates. Well, if you change the value of d, you're going to change this subgroup, the one that doesn't involve sigma, and so you're going to get a different subgroup S. But if we fix d, the situation is different for different values of k. There may be duplicates. because if you, for example, add to k n over d, it'll be rho to the k times rho to the n over d. The rho to the n over d gets absorbed in here, and you don't change the subgroup. So you changed the exponent, but you didn't change the subgroup. So to be more specific, if we take our exponent k and we divide by n over d, we get this, the division algorithm, r is in this range. Then if we replace rho to the k by rho to the qn over d plus r, rho to the qn over d gets absorbed. It's an element of this subgroup generated by rho to the n over d, so this reduces to rho to the r. So we can restrict k to the range of the remainder here, 0 to less than n over d, without losing any subgroups. Also, these subgroups are distinct. Now, because if j and k are in this range, we can assume j is less than k, and if these two portions of S are the same, that implies that rho to the k minus j belongs to this subgroup. But the problem is this exponent is smaller than n over d, so no multiple of this is going to give us this one. So rho to the k minus j is the identity, or equivalently k equals j. And so these are all distinct. This description of the subgroups give you a complete list of distinct subgroups if we restrict k to the range 0, greater than or equal to 0, less than n over d. So, summary, the subgroups of the dihedral group D2n are of two types. For each d dividing n, we have the cyclic subgroup rho to the n over d, generated by rho to the n over d, has order d, and then we have these subgroups that are half in and half out of the gigantic subgroup. And this subgroup is also generated by these two elements. And I'll leave you to sort out this equality here. These subgroups have order 2D because these two have the same size, and this has size D, or order D. Also, each of these is dihedral in its own right. Each of these is cyclic. Each of these is dihedral. And that we still need to prove. Okay. But the subgroup SDK here is generated by this element, which I'll call alpha for convenience. It has order D. And this element, which I'll call beta, and it has order 2. Moreover, we have the following commutativity rule. Alpha, beta, just fill in what alpha and beta represent. I want to move rho to the n over d across the sigma, and it becomes rho to the negative n over d. And I can then push that past the rho to the k, so I write it this way, which is beta alpha inverse. So this subgroup fits this standard template, and that is the dihedral template. So each of these subgroups is in fact a dihedral group in its own right. Okay, there's another sheet of paper. Here we go. Well, we figured out the subgroups of the dihedral group. They're sort of interesting. There are the cyclic subgroups of the gigantic portion of the dihedral group generated by the rotation, and then there are those that are split in two, and those are dihedral. What about the normal? So which ones are normal? This is a natural question to ask. Well, the cyclic subgroups are normal. This subgroup is closed under conjugation by rho because its generator is. If you take any power of this and you conjugate it by rho, it doesn't change. But it's also closed under conjugation by sigma. So we take the generator and we conjugate by sigma. Again, we push the rho to the n over d to the right of rho inverse, of sigma inverse. We get this, which belongs to the subgroup. So these subgroups are normal. It's not quite as simple for the subgroups that get split in half by the gigantic subgroup, the SDKs that look like this. As far as conjugation of this first generator, we've just seen that we can conjugate this generator by either rho or sigma, and it remains in this subgroup. Where to go here? So it remains in SDK. We have to examine what happens when we conjugate the other subgroup, the other generator, sigma rho to the k. Conjugate by rho looks like this. Again, move the this rho across this sigma. The sigma remains intact. The rho becomes rho inverse. So we've got a k exponent, -1, and another -1. So we've got rho to the k minus 2. Break that up this way. And this does lie in this subgroup SDK. Okay. Oops, I have SKD here for some reason. Okay. I'm sorry, I didn't complete the sentence. This lies in the subgroup SDK if and only if rho to the -2 lies in this subgroup, because sigma rho to the k does belong to the subgroup. So we need the other factor, rho to the -2, also to belong to SDK. Okay. And that, of course, is equivalent to saying rho squared is in SDK. Okay. But that holds if and only if rho squared is in this portion of the subgroup. It can't be over here because there's no sigma in rho squared. Well, for that to happen, rho squared has to be some power of rho to the n over d, and that's only going to happen if n over d divides 2, which means that n over d is either 1 or 2. If n over d is 1, then SDK is generated by sigma and rho, and so it's the full group, the full dihedral group. If n over d is 2, then n's going to have to be even. K is in this range, which means k is either 0 or 1, and we get two different subgroups, generated by rho squared and sigma, generated by rho squared and sigma rho. So the normal subgroups of D2N are of two types. All the subgroups of the cyclic group generated by the rotation, this is the gigantic subgroup, and for n even, there are two other subgroups. They look like this, but these have order n, so they are gigantic as well. and therefore obviously normal. Okay. Now I want to analyze another family of group templates, and this is for several reasons. First, this template family defines an important class of groups called the dicyclic groups, dicyclic. Second, the dicyclic group of order 12 is that fifth group of order 12 I mentioned earlier. We discussed groups of small order, and I said that groups of order 12 are going to give us the most trouble. There are 5 of them. 4 of them are very familiar. 2 of them are abelian. There's an alternating group and a dicyclic group. A dihedral group. And then this 5th one was a little more mysterious. It's a dicyclic group. And third, the analysis we're about to do actually describes how it is possible to leverage existing valid templates to show that other templates are actually valid as well. So here we go. The template that interests us is this template. 2 generators, order 4n. Order of A is 2n, order of B is 4, and we have this commutativity rule. And this is for n bigger than or equal to 2. And so I'm going to call this a dicyclic template. Well, there's one for each n, so it's a family of dicyclic templates. This isn't a standard template because the product of these 2 orders is bigger than the order of the group. This would be 8n. So we can't just simply rely on what we know directly about standard templates. Let's assume for a moment that a group H fits this template. Now the cyclic group generated by A has order 2n, which is half the order of the group, so this cyclic group is a gigantic subgroup of H. So it's normal in H. The subgroup generated by B is therefore, since it's not contained in the subgroup generated by A, because then B would be an unnecessary generator, and we wouldn't get order 4n, we get order 2n. So that subgroup must be cut in half by this gigantic subgroup. The intersection of these 2 subgroups then is contained, of course, in the subgroup generated by B, and so it has size, and this has size 2, because the subgroup generated by B had size 4, and this cuts it in half. So this has order 2. It's contained in this subgroup. Probably should do a strictly less than here. So that implies that the only non-identity element of this intersection I has order 2. But A to the n is the only element of this subgroup that has order 2. And B squared is the only element of this subgroup that has order 2. And so these have to be the same because they belong to I. Okay? I has a single element of order 2. And that element has to be in both of the participants of the intersection. So we get this relationship. Okay. So we were able to get from this template to this relationship, which is not an obvious path, by using the gigantic subgroup theorem. So we can replace b squared with a to the n, and that tells us that the elements of H, all the elements can be written in this form: a to the I, b to the j. I ranges from 0 to 2n minus 1, because A has order 2n, and j is either 0 or 1. If j were 3, we could use, so b to the b cubed could be written as a to the nb. So we can reduce the exponent of b. These 4n elements are distinct, and I'll let you ponder that. And so they actually constitute the underlying set of H, assuming H exists, of course. So if there is a group H satisfying the template, this must be its underlying set with no duplicates. Also, the product in H then comes from this commutativity rule, and so it looks like this. It's what we've seen for the standard template. The commutativity rule is the same as one that belongs to the standard template, so we still get this property. When you move this b to the j across the a to the k, the b to the j crosses unaffected, but we have to take the k here and multiply by what we used to call t in the standard template, t to the power of j. So that's what this term is here. Okay. So if H exists, it's got to have this underlying set and this product rule, so it's unique. For the case n equals 2, which is one of particular interest to us, the template then can be written in this form: 2 generators, order 8, that's 4n, order 4, also order 4. This is order 2n, so that's 4. This is always order 4 in all the dicyclic templates. This is the commutativity rule, because 2n minus 1 is equal to 3. And we now have this fact that comes from here: a squared is b squared. And I put it in parentheses because it is derivable from the rest. So I think this is a good idea, because if you were presented with this template without the parentheses and asked, is it valid, you would be looking for a group that fit 1, 2, 3, 4, 5 conditions, not knowing that you don't need to check this condition because it comes from the others. So, it's a practical matter. And, I suppose there are other templates that you might write down where one of the conditions follows from others, and you wouldn't know it until you checked. But since we did check in this case, this is what you might refer to as an optional relation. You leave it out, you get the same template. This template is actually equivalent to the quaternion template, this one. And we talked about this in example 621. So to see this, suppose first that G generated by A and B fits this dicyclic template. To check the G also fits the quaternion template, all we have to do is observe. We have here same group order. Okay. What we need to check is that this relation holds. So we write AB, AB, associate it this way. BA becomes A cubed B, because that's allowed, that's part of the template, and that's a to the fourth B squared, and that's equal to B squared because A has order 4, and that's equal to A squared because of this relation we derived. So that is precisely the relation in the quaternion template. But we know that the quaternion template has only one, uniquely determines a group. It's the quaternion group. So G, the group that satisfies this template, has to be quaternion. So the group that fits this template also fits this template. So let's confirm that the quaternion group fits this template. That if it fits this template, it fits this one. Well, we can do that with the quaternion matrix group, because if Q is any quaternion group, it's isomorphic to the quaternion matrix group. And so we've got matrices that help us make sure that all of these conditions fit. Okay. So Q is generated by the matrices A and B, and the rest is just a matter of checking that the order of this matrix is 4, the order of this one is 4, and that BA equals A cubed B. So I will leave that for you to do if you're interested. To further understand the general dicyclic template for all n bigger than or equal to 2, note that these templates have some features in common with the standard template, T2n for 2n minus 1. So I put the two templates next to each other. And the generators, there's 2 of them. A has the same order in both templates, B has the same order, the commutativity rule is the same. The only difference is in the order of the groups. Now we know that these templates, the standard templates, define a unique group G of order 8n. And we can use such a group G. It's kind of strange to say unique group and then say such a group, but it's unique up to isomorphism. So it's not truly unique. We've discussed this issue before. Actually, what I should have said was essentially unique. It's just that you will hear this term unique group without the word essentially, and so you have to always keep in mind that in this setting of group theory, unique might mean unique up to isomorphism. People like to be sparing of their words, use as few words as possible, so they will lapse into saying unique group when they really mean unique up to isomorphism. Okay. So how do we use one of the groups that fit this template to find a group that fits this template? Well, so one way to obtain a group of size 4n from a group of size 8n is to factor by a necessarily normal subgroup, n, I'll call it, of size 2. That cuts the quotient groups in half the size of the original group. It will then have size 4n. Now, an advantage to passing to a quotient group G mod n is that the coset product rule sort of mimics the product in the original group. You multiply or take the inverse of a coset representative. Okay. And so the commutativity rule will hold in the quotient group, and it looks like this. This is the commutativity rule in the full group. I can use both of these as coset representatives for n, and then the coset product rule means I can push the n over, so bn an, that's equal to ban, and this is equal to an to the 2n minus 1 bn. This then is the same commutativity rule for the quotient group G mod n. But we still have to arrange it so that an and bn, if we want those to be the generators of the group that fits the dicyclic template, we have to make sure they have the correct orders. But since an to the power 2n is equal to a to the 2n n, which is equal to n, and bn to the fourth power is equal to b to the fourth n, that's n, all we need to do is show that a to the 2n minus 1 is not in n. See, this tells us that 2n is an exponent of this coset, and 4 is an exponent of this coset. We have to make sure that it's the order, so we have to make sure that a to the 2n minus 1 does not belong to n, and that b cubed does not belong to n, because that would potentially, that would reduce the order. So this is something still left to be done to make sure that the orders, to guarantee that the orders of an and bn are correct to fit the template as generators. Okay, well, we still haven't found n, so we need to find n. It's a normal subgroup of size 2 for which this holds. One place to look for normal subgroups is in the center of the group. So let's take a look at the center. What is the center of the group G that fits the standard template? Well, an element of this group is of the form z equals a to the I b to the j. I is excuse me, I is in this range, and j is in this range. It will be in the center of G if and only if it commutes with the two generators A and B. Excuse me for a moment. As far as commuting with B, we have a to the I b to the j b. That's equal to a to the I b to the j plus 1, obviously. We did nothing here, really. If I put the b on the other side, I get b times this element, and now I want to move this b across the a to the I. The b goes across without change, so I'll have b to the j plus 1. The a to the I becomes a to the I times 2n minus 1. Because this is b to the first power, so I don't raise 2n minus 1, or I raise it to the first power. Okay. So equating these two, there's a lot of cancellation here. These will be equal, and b will commute with this element. If a to the I equals a to the I 2n minus 1, that holds if and only if n divides I times n minus 1. But n is bigger than or equal to 2, so these two numbers are relatively prime. And since I is in this range, this condition will hold if and only if I is 0 or I is n. So z is b to the j, or z is a to the n b to the j. As to b to the j commuting with a, Well, we have b to the ja is equal to this. We use the commutativity rule here, which is ab to the j when j is 0 or 2, and a to the 2n minus 1 b to the j when j is 1 or 3. I'll let you fill in any details there. So b to the j will commute with a if and only if j is 0 or 2. As to the other choice here, a to the n, b to the j, commuting with a, and we can now restrict to j equals 0 or 2, but in any case it doesn't matter. When you compute a to the n, b to the j, a, you get this. Compute it in the other order, same thing. So there's no issue here. So the elements in the center are given by this for j equals 0 or 2. So this is the center. And I'll leave you to verify that if you wish. Notice that every element in the center that's not equal to the identity actually is an involution, and so this is a familiar group of order 4. This leaves us with 3 choices for a normal subgroup of order 2 that lies in the center. We take the identity in any one of these 3 involutions, and it's not difficult to see that for any one of these choices, we will have this property here, which is what guaranteed that the cosets an and bn have the correct order. An has order 2n, bn has order 4. I'm sorry if that was not in the camera view. Here it is. So any one of these quotients, G mod Ni, fits the dicyclic template, which is what we were trying to do. Actually, when n is odd, bigger than or equal to 2 and odd, the dicyclic template is equivalent to this standard template. And I will leave it for you to show that these two are equivalent. So we have the theorem for n bigger than or equal to 2. The dicyclic template defines a unique group called the dicyclic group of order 4n, which we'll denote this way. When n is odd, the dicyclic template is equivalent to a standard template. I left that for you to show. When n equals 2, the dicyclic template is actually quaternion. So the dicyclic group is the quaternion group. And when n equals 3, this template, which is equivalent to this template, defines a unique group of order 12. And later on, we will show that it is not isomorphic to A4, which has order 12, or the dihedral group D12. So we do have a fifth. It's non-abelian, so we do have a fifth group of order 12. We'll also have to show that that exhausts the catalog of groups of order 12, which we will do later on.